Okay, it's me again, Jean-Louis Van Bella. I want to do a video on a topic actually I thought I had closed more or less. It's on the proton puzzle, as they call it. In the last few years, one of the great breakthroughs was that they have measured the observable properties of a proton very, very precisely. Not only better measurements of its magnetic moment, but especially of its radius, its charge radius. So that has led me to produce, well, basically this paper where I said now we could, build a model for, well, not the electron model. This is my electron model. But basically for a proton model here, the other one. The electron model, I sort of consider that to be ready. I'm a fanatic of, or let's say an admirer of Zitterbewegung theory, which revives an interpretation of Schrödinger himself, of his own wave equations, where basically he says elementary particles, like electrons, or a proton in this case, but he talked mainly about electrons, are probably, they have a structure, and that structure is probably a point-like charge inside the electron, tittering or moving around at, well, the speed of light. So that model for an electron, which you saw on the screen now, I thought we can probably extend that to a proton. So I wrote many papers and honestly spent a lot of sleepless nights trying to work out that model. And it works and it doesn't work, and I sort of gave up, I guess. But then I didn't. Let me go through this paper maybe after the introduction is. Let me show the equations. Yeah, so basically, you need a model. As I said, the electron model is a planar model, is like motion in 2 dimensions. If you want to think about, charge moving or oscillating around in 3 dimensions, you will naturally represent that problem in spherical coordinates. And I don't know if you can see the equations here. But that's what they are basically. These are Cartesian coordinates expressed in terms of spherical coordinates, a radius and a polar and azimuthal angle. You can see that here, x, y, z is equal to, r times the sine of the polar angle, cosine azimuthal angle, r sine sine, and r cosine of the azimuthal angle. And then you can do a lot of things. We see here we left it to ChatGPT to calculate. Well, we didn't leave it to them, but it's and that's also what I want to talk about. It's been very, very rewarding, and it really led to, well, this breakthrough also, where you can intelligently converse with ChatGPT. And what I found is that unlike last year, ChatGPT 3, ChatGPT 4 is very spectacular at creatively suggesting things you might do and think about, and also it's amazing at actually visualizing this kind of complex motion. If we talk about complex motion, I have here Desmos, an easy grapher. The electron model would be this blue thing, huh? The radius of this oscillation, which we interpret as an orbital oscillation, not a linear. So we have a point-like charge inside of an electron. That is the hypothesis. Its radius is not infinitely small. Hard scattering suggests this radius of that blue ball is actually the classical electron radius, the Thomson radius or Lorentz radius, and the radius of the oscillation itself. The sphere you see here would be the Compton radius, so that would be the interaction radius between the electron as a whole, the structure, and incoming photons. So that's the hypothesis. So moving to a proton model, then we should imagine, of course, because the proton is much smaller, so you should imagine the sphere is a lot smaller than the Compton radius of a proton, and we would have some kind of motion in 3 dimensions, which basically, if you look at my formula here, let me pull up my notebook. That might be easier because I summarized that. That would be this. simply the spherical coordinates, and then what we will do is, because the Planck-Einstein relation tells us, there's some frequency, and there's a unique frequency. That's where my electron and proton models differ from all others, I would say, from nice colleagues that I have. But they usually have a model which involves, two frequencies, some kind of a toroidal model, or yeah, something that looks like that. Two frequencies. I said, there should be only one frequency, and the question is, how do you distribute that frequency over your azimuthal and polar angle? Because that's how the frequency is going to come. Your radius in this model. We could have a varying radius, a proton model with a varying radius, but so we're taking first steps, and so we think the radius is not gonna change. We want a spherical model. The measurements assume that, and also packing models in an atomic nucleus. Yeah, they suggest neutrons and protons are kind of spherical things. So that's how we start, basically saying, okay, instead of an oscillation in one dimension like an electron, which leads to circular frequency, circular orbital, will have two-dimensional oscillations actually in 3D space with two frequencies. Well, one frequency but distributed over an angular and an azimuthal angle. We have two angles rather than just one. So that gives rise to what you see here, this thing, how we can sort of play with the parameters, and we did that. The problem was when you work out really the formulas for the angular velocity of that thing, and also the tangential velocity, we arrive at funny things. The hypothesis in the Zitterbewegung model is actually that a point-like charge in an electron, for example, has no rest mass, and that sort of all the energy is either kinetic energy, or you could say potential or electromagnetic energy, because this charge in motion generates an electromagnetic field, the magnetic moment of the electron or the proton. Now, relativity theory tells us that, yeah, we have a charge, but it's like photon-like in the sense that it has no rest mass. So its velocity should be equal to the speed of light, just like a photon, no rest mass. And so it sits around at the speed of light. At speed of light, exactly. And that's something where, we get, let's start with the orbital velocity. Or angular, let's say, let me use correct, the angular velocity. So I have this omega, all right? I won't go too into the detail. You can look up, 3D motion engineering, but you arrive at a formula, you can write this omega, the angular velocity, in terms of, your spherical base vectors, one related to your radius vector, one related to your polar angle here, and one related to your azimuthal angle. Let me clean up my sheet, my whiteboard. So that looks like a horrible, complicated thing, but with this very simple linear function that we choose, linear dependency on time, you can calculate the time derivatives that we have here, and they're all equal to w, this w, right? So that simplifies the expression an enormous lot. I did that in the paper. Here I simplify that. Let me do this lecture here. Or have it here. I calculate this thing, right? And you can sort of see, we're applying the standard formula of for the magnitude of a three-dimensional vector here, and we arrive at this result. I have here sort of a weird omega bar instead of a W, which is simpler to use. But you arrive at this result, right? That we have a constant magnitude of this angular velocity vector. I will talk about its direction, the other thing, in a moment. But that was a nice result where I said, whoa, we have a nice constant angular velocity. Then the tangential velocity, the speed with which this thing travels on the sphere of the surface, that is a more complicated equation. Well, not more complicated, it's the same thing. You can sort of well, you can ask ChatGPT. I will talk about ChatGPT in a moment, how it helps to solve these kind of problems. But you can again write it in terms of your spherical base vectors, and you arrive at the time derivative of your radius multiplied by the radius base vector, and the base vector related to your radius vector, and then this minus and a plus. Let me clean up to show you that. Now, what you can see, and this is the puzzling thing, is that the time derivative of r is 0. The radius vector is constant. It's just the radius of our sphere. So this thing disappears. Where is this popping up? It disappears, and you arrive at this formula here. R times W times the base vector related to the polar angle, and then here, and this is interesting, R times W times a sine of the polar angle. Now, when you write that out and you say like, okay, I want to take the magnitude, I want to calculate the magnitude, then we have the same thing. I will show that again in my calculation here. It's there. No, that's going to be okay because I didn't go there. I think I went here. On this remarkable result, we get a variable, here. We get a variable velocity for the tangential velocity. We actually get this result that the tangential velocity varies between a minimum of r times, a maximum between r times w, and sorry, a minimum, because this is 1 plus sine square and then the square root of it, and a maximum given by, when the polar angle is 90 degrees. So the interesting thing that was very puzzling, and I thought like this is not consistent. We get a non-constant tangential velocity while relativity theory, or at least these basic Schrödinger hypothesis tells us if you're really going to assume that a proton is a structure consisting of a small but not infinitesimally small point-like charge zipping around in some kind of a 3D trajectory that we have here. And you can see it's a curious double loop like thing. It's very interesting, and that's also what I explored. And it gives rise to what kind of magnetic moment would this generate, and is it consistent with the magnetic moment that we measure for a proton? These are all interesting remarks, and I arrive at a few simplistic models, indeed using square root factors and sort of an effective radius, because if you can see, this double loop is like has a radius when you view it along the z-axis, which is half of the radius of the sphere. You actually arrive at very consistent results, theoretical results that are consistent with the real-life properties of a proton, its magnetic moment, and again, its radius. But the basic result that we have here, that this point-like charge would zip around at a speed that is not constant. You can't see it here. It varies between, like, if we normalize between 1 and 1.44, something like that, a square root factor that is in there. It varies, and you can't see that very more, but it goes fastest when we do this here. It goes fastest when it reaches the not the when it's on the equator. The equator is shown here, but sort of at the pole, at the North Pole, let's say, here on this thing. There it goes a bit faster, and you can also see and appreciate that the motion here is more linear than circular, so that has implications for sort of when you calculate the magnetic moment, or you would calculate the magnetic moment of this thing. This is not easy. There's no standard formula for calculating the magnetic moment of a Zittering charge like this, motion like this. But so let's go back to the main problem again, and that's sort of this varying tangential speed. The interesting thing, and that's where I started chatting with, now I'm going to pull it up, with ChatGPT. It's an enormously long conversation, but we arrived at the conclusion that, this inconsistency may not necessarily be bad. In fact, we arrived at the conclusion that maybe the assumption that we have a Zitterbewegung model for the proton, just like we had a Zitterbewegung model for the electron, some really tiny point-like charge is not appropriate for the proton model. We might think of the proton being like a sort of a blob of charge, and charge might be distributed and not concentrated in one single point-like charge moving around, but all over. And then we would have a varying tangential velocity as we have here for each point on this blob, and we can discuss if it's a spherical blob or if all the charge would be a shell, the shell that is described by the sphere. But different points on or in this blob might momentarily move faster or slower. And so it would kind of violate, strict interpretation of relativity theory, saying like, charge in itself has no other properties but charge, but it would maintain sort of the overall consistency in that system. That's a complicated thing to talk about, and it's really sad that I can't share the chat here. Let me try it again. Yeah, because I uploaded a lot of images, and it's that it's apparently not user supported, which is not so bad because I want to keep my secrets, of course, and then I hope it can it pushes you to explore similar questions as the one that I'm gonna show here. Let's go back to sort of the interesting thing about this calculation of let me clean up my sheet again. Yeah. There we are. Is that this tangential velocity? I said it's not constant, but it does consist of two orthogonal components, and that is a very interesting thing. There's one component that is written in terms of the polar base vector, and one in the azimuthal base vector, the base vector related to the polar and azimuthal angle respectively. That's the correct title. One has a fixed magnitude, r, I said, r times w, and the other one has a variable magnitude. And now that is interesting because the problem really that we have here is what I write down here. In a 2D Zitterbewegung model of an electron, this formula holds, where the tangential velocity, as said, is equal to the speed of light, to the light speed, is equal indeed to, the angular velocity times a radius vector, but the radius of a perfect circle. And so there's no variability in that. Why? Because these three vectors in this circle that you have here, let's assume this is our electron, much larger than our proton, but I can't make it too large here, that these three vectors are perpendicular or orthogonal one to another. Now, as said, when we move these results here to a 3D model, and we have indeed this rather simplistic linear function, but for instinctive reasons, I believe it makes sense because it introduces one single frequency, the idea of a single frequency, a single de Broglie frequency or Planck-Einstein frequency or whatever you want to call it. But that's quite essential in, I think, de Broglie's or de Broglie's hypothesis of a matter wave and the Planck-Einstein relation, which applies both to light-like and particle-like, particles. Or matter-like particles, I would say. I will refer, I'm probably rambling now, and I hope it doesn't do, I might have switched off. But what we have here in this case is that these formulas show that the tangential velocity is not, it is a product of the angular velocity times the radius vector. Let me clean up here. So the formula applies, but these three vectors are not orthogonal one to another. And so again, that for me was puzzling. But I said I chatted with ChatGPT a lot, and it shows indeed that in this interplay between the angular, let's say the polar and azimuthal component of the angular velocity vector, that play is comes when you go from 2D to 3 dimensions. It's not a mere generalization, and your interpretation of an angular velocity vector becomes a little bit different. It has constant magnitude, but it also results indeed in sort of when you're gonna try to decompose your tangential velocity into other vectors. that you would think that they are perpendicular. Well, we get another decomposition here. This one here. We have two orthogonal components, but they're the two orthogonal components are related to the the base vectors that are related to the polar and the azimuthal angle. So that's still puzzling, but it's encouraging where you then can indeed imagine a sort of a blob-like structure. Not a point-like charge, but a blob. And then you that variant tangential velocity again, that would sort of reflect the internal dynamics within that blob. It is a difficult thing to think, because then you have, and now I'm gonna go to my discussion here, is then you say like, oh wow, this is gonna be, you know, when you think calculating the magnetic moment and kinetic or potential energy. I said we have the equipartition theorem in these things. Yeah? Half of the energy of a proton, or I would say the equivalent energy of the mass as we measure it, would be in the kinetic energy of these, the blob of charge, or the point-like charge, or all the little points of charge on that spherical or shell-like structure. And yeah, that the half of the kinetic energy, we have a distributed charge system here. Then we can apply the formulas, but and give general integrals that we should use. Where I said, yeah, first relativity comes into play. We need that energy equipartition theorem. To be honest, we didn't get out of the discussion, but ChatGPT gave very nice. Simplifying assumptions, I would say, where it said like, okay, we need to explore perhaps when we go from a point-like charge zittering around to a blob-like structure, where the different components, or the charge within the charge, the blob charge, have different velocities and varying velocities. Then we need to make assumptions about the charge distribution on that sphere or on that spell, and it really made fantastic or worthwhile suggestions, where honestly I need to say I need to check these carefully, and unfortunately I don't have the time for that. But I will do that probably over the coming weeks or months, and I encourage you to engage in a similar discussion, because I have a feeling in this kind of discussions we may solve the what I call the proton puzzle. We've measured, said its properties, but we still don't have a consistent model. One of the discussions I want to show is that at first we wanted to sort of say, okay, we have uniform charge density. Perhaps I said, well, no, it's probably going to be, and the charge density would then be constant. I said, no, we need to average over a cycle. When you see that, you can clearly see in a structure like this charge content. If we generalize that point-like structure to some kind of blob moving it, we can average charge densities, and these would probably be constant and help in the calculations. But a uniform charge density, even for when we move from a point-like charge zittering around to a dynamic blob of charge, uniform charge densities are not going to make sense. And so we refined definitions that went very well. I found ChatGPT's conversational style incredible, and I also want to add here, I said last year ChatGPT 3 would not have been able to do what it does here. This is clearly at the level of, I would say, a PhD student in physics, and it's got it. I mean, it's not coming up with but it tries out things. It's suggested also to visualize things. It has done visualizations in the past of charge densities, really very interesting stuff. I restrain it a bit here, because I first want to have like more of a qualitative exploration of this model before we do these calculations and see if they're consistent with the calculations I did in this paper, which are heuristic, I would say. Let me show these if I have them. Here, perhaps a sphere or a shell of charge. I explored that hypothesis. That's concluding remarks. I don't have the calculations of. But here I started experimenting, with concepts like an effective frequency, an effective radius, and it gives me what you see here, the proton radius as measured by Jefferson Lab's PRAT project. And it also gives me, but that's not so much in here, perhaps in the annexes, the magnetic moment, where I think I asked ChatGPT actually to provide, yeah, here, a summary of my calculations where I explored, maybe the impact also of precessional motion. And yeah, I'm getting at consistent results using very standard assumptions of, for instance, this one, that if there is precession, the precession would be determined by the energy equipartition moment itself. It would pack 1 unit of the quantum of action of yeah, Planck's quantum of action. So all these movements, as soon as you insert another degree of freedom in motion, you need to use quantum theory, like I think it was originally intended, and that's sort of to see this motion. How many does it pack a unit of Planck's quantum of action, and how does it do it exactly in a 2 or a 3-dimensional motion, and get frequencies out of it, and make sure that everything adds up in terms of energies. I'm gonna stop rambling a bit, maybe by just going on this thing where I also said, like, okay, one of the things, if you start doing like that, is you need to respect that axis, or I would say this plane of symmetry that clearly you can see. This is the what I uploaded, and apparently prevents me from sharing the chat. So you clearly have an axis or a plane of symmetry in this motion. The plane of symmetry would be, let me see if I can rotate this a bit differently. Yeah, the plane of symmetry would be the here you have it. What sort of cuts this double loop into 2 single loops, I would say. So you see it making a loop on the northern hemisphere, and then you see it making a loop on the southern hemisphere. Looked at it from this side, it's clear that it's going to generate just like a ring current, but this is sort of a, think of one loop that is split into 2, like this. I should maybe show again my yeah, it's not so clear, but you have 2 loops. They have the same orientation, so it would would generate a very strong magnetic moment in. Let's see it again. It's kind of slow for me to play. I also don't know how to move it. Yeah, but here you can see it. The orientation of the 2 loops, you see it going gray in the background, and when it goes from the side we are looking at now, let's say the northern hemisphere, to the southern hemisphere at the back, and you see the orientation of the loop is very strong. So along this axis that we are now looking at, the north-south pole axis, the magnetic moment would be very, very strong. You can really compare a little bit with the Earth, which has a magnetic moment or orientation between the north and the south pole. But it's a very different geometry, of course, and the symmetry is also very different here. But that's the idea, and the amazing thing is that ChatGPT goes so fast. It already offers formulas that I would need to look at if they are. So it modifies then charge densities to arrive at sort of an approach to solving these integrals, which is we know that solving integrals is not easy in physics. Probably the thing where a human genius or a PhD student might still have an advantage over ChatGPT. Also, although when I see what it does here, I don't think so. I mean, I couldn't quickly sort of suggest like, oh well, let's make this simplifying assumption, and then our integral becomes something like that. The interesting thing was that every time it suggested something, I said, yeah, can you sort of translate this back to kinetic and electromagnetic energy? I said kinetic energy of these charges that are moving about. And the electromagnetic energy that it generates, the energy in the field, does it slosh back and forth like it should be in a classical, both non-relativistic and relativistic oscillator, regardless of how many degrees of freedom that you have, if it's a one-dimensional oscillator or a two-dimensional one or a three-dimensional. And it suggests it does. I mean, I would need to look at all these um, formulas it generates here, because ChatGPT can make mistakes. Check important info. I haven't seen it doing mistakes, but I do remember even this conversation started again with sort of making sure that the conventions we use, is it engineering conventions, what is the orientation of our tree model, what do we define as the polar and azimuthal angle, and how do we define it, and does it vary between 0 and pi or 0 and 2 pi? I need to define that for both your polar and so we spend some time again on just agreeing on the symbols that we both use when we model stuff like that. But it did marvelous. It wasn't able for some reason to generate graphs, but I can do that with Desmos. It looks great. I think this assumption, or let's say, of course, I will admit this is like saving my model, right? Saving my proton model. I get an inconsistency, and then I arrive at saying, well, this assumption could, resolve that inconsistency. I do honestly believe that it's more than just trying to save my model. It is a good assumption, because if you think of it, a proton, we have no evidence. With an electron, we have Compton scattering and Thomson scattering, right? Hard scattering and elastic scattering. A photon interacts with an electron, and it will lose energy, or it won't. It will just be scattered off elastically, or else it will lose energy, and we get an outcoming photon with less energy. And you can explain that by modeling indeed an electron as a point-like charge zittering around, because the photon could hit the charge itself, or it could sort of mess with the electromagnetic field that this charge generates. And then you would have a complicated model where the orientation of the plane of oscillation of that point-like charge would be very important, and would be random, of course, statistically deterministic, as I said, not indeterministic, but statistically deterministic. But it explains Compton versus Thomson scattering. With a proton, we don't have any evidence that there are like two kinds of photon scattering or other particles. Actually, a radius is measured by particle on matter particle on matter particle scattering, not by firing photons into it. But there's no evidence that there is something like soft scattering or elastic scattering versus elastic scattering. So modeling the proton as a blob of charge rather than an empty structure in which you have this circular motion going on, that makes sense. That is consistent with all projects. And the fact that this first inconsistency we got out of the model while trying it to model as just like we modeled the electron with a point-like charge suggests that that wasn't correct. We need to think about the blob. Now, this would be a PhD topic, I think, for researchers. I will keep following it. If I have time, I will engage again with ChatGPT, but first I need to review what it generated now. But that's been an interesting exercise, and so I want to keep sort of pushing the boundaries of what we know about the proton now, and then sort of further dive into reconciling, I would say, these inconsistency velocity with dynamic energy distributions, both kinetic and electromagnetic, as we have in this 3D model. So I will continue to work. The dynamics are interesting. We should better relate them to experimental observations and arrive at very precise calculations, not as the intuitive ones, where I say, like, I have very simple. One scientist called this is a bit numerology, isn't it? Yes, but if you have a discrepancy involving a square root 2 factor, then you can apply Feynman statement saying, like, if your model is that precise, if your calculations are that precise, they probably do say something very deep about what is actually going on. So that will be it. Let me see at where I am, and if I have other things to show. I'm at 35 minutes. That's a bit more than the half hour I had planned, but that's okay. Maybe just in terms of a form, I actually played 2 hours to have ChatGPT generate a, um, a structure for this conversation, um, which I can show, and it did really wonderfully well. And then I tried with 11 labs to generate a voice and images, and I tried video generation applications. But in the end, I ended up doing what you will probably not like, is just take my whiteboard, jot a few formulas down, and then navigate between websites, your papers, what you did with Desmos, and use the script that ChatGPT generated for this speech or expose or lecture or whatever you want to call it. So thanks a lot, and that will be it. Thanks a lot. It's I said I don't have much time, but I wanted to touch touch upon this again. As yeah, this night I woke up with, yeah, there's something in that. Let me immediately talk with ChatGPT and expand our conversation into this. And I think it's nice. It shows how you can play with ChatGPT, use it intelligently, and not all of what it says might be correct. I need to check it, but it's sure a very useful tool, and it doesn't hallucinate. ChatGPT 4 doesn't. ChatGPT 3 last year would definitely hallucinate on things like this. But no, GPT has come a long way. And with that optimistic message, I think in some kind of interaction, not between me perhaps and GPT, but many researchers who are into these topics, maybe ChatGPT and you might resolve and the proton puzzle by coming up with very strong analytical results that show that this model, when we apply it to sort of a blob of charge, uh, generates the magnetic moment, the radius of the proton, the charge radius, exactly, not approximately, but exactly. And then these exact formulas, integrals, and whatever should be, yeah, we should be able to summarize them in these more intuitive, or let's say heuristic formulas that I found here, and let GPT summarize in this paper, Building Blocks for the Ultimate Proton Model. Thank you very much for listening, and I hope to see you next time. Have a nice Sunday and a nice week, and a very happy 2025.